So find the distance of object from a concave mirror of focal length 10 centimeter so that image size is 4 times the size of the object. So that image size is 4 times the size of the object. If you just join, there is a question. And the question is that find the distance of objects from a concave mirror. Find the distance of objects from a concave mirror of focal length 10 centimeter so that image size is 4 times the size of object. Okay. Find the distance of objects from a concave mirror of focal length 10 centimeter so that image size is 4 times the size of the object. This is the problem of the evening. So quickly go through it. You have 5 minutes left to finish this. After which we'll all discuss, okay, to see our strength and then our shortcomings.
Sir.
Hello.
Please, good evening.
The evening is so good, Angie.
Please, I just joined. I didn't know you were giving a question.
So find it. This is the question. Find the distance of objects.
Recording in progress.
Find the distance of objects from a concave mirror of focal length 10 centimeter so that image size is 4 times the size of the object. Find the distance of object from a concave mirror of focal length 10 centimeter so that image size is 4 times the size of the object. Angie, this is the problem, okay, on the drawing board.
Okay. Thank you.
Welcome. Somebody is getting you to be 2. 2 centimeter, I doubt. You have 3 minutes more. 3 minutes. Somebody is getting 5 centimeter. Ella, what's your answer?
Sir, please, I got 12.5 centimeters.
That is not enough. Evelyn, what is your answer?
Sir, please, I'm on it.
Okay. Somebody, Ella, okay, 12.5. Ella, that's not all. Augustine, look at your value again. Angie, look at your value again. Something is seriously wrong. Okay, I think our time is up. Your time, your 6 minutes waiting period is up. Let's look at how to go about the question. Okay, so Abinema, please mute yourself. Abinema, we are getting feedback here, okay? So find the distance of object from a concave mirror of focal length. So at least we know that the focal length of the mirror is 10 centimeter. Okay, somebody is also sending me. Okay, the focal length is, so let's discuss it. Ceasefire and let's discuss it, okay? The focal length is 10 centimeter, so that image size is 4 times magnified. So we know that linear magnification is equal to 4. 4 times the size of the object. What kind of mirror is involved here? What kind of mirror is involved here? Class, let me hear from you. What is the type of
A
mirror?
Converging mirror.
Converging or concave? Good. So these are things you must look out for. What is the nature? Kingsley, please mute yourself. What is the nature of the image formed here? What's the nature of the image form? Is the image real or virtual?
Real.
What is that statement in the question which, indicates that the image is real? Is there any information in the question which shows that the image is real? It's a question to all of you. Is there any information in the question which shows that the image is real? Is there any information in the question which shows that the image is virtual? Class, is there such information?
No, sir.
There is no such information. Meanwhile, a concave mirror or a converging mirror forms an image, a real image, which is magnified, and also forms a virtual image, which is magnified. So because we don't have these details to clearly tell that the image form is either real or virtual, we must consider it when real and when virtual. So when the image is real, when image is real, so we are answering it this way because the convex mirror forms a magnified image which is real and which is virtual. Just the magnified, the statement magnified is not enough to tell you that the image is real or it is virtual. So you must consider it when real and when virtual. Is that okay? So when real and using RP, we have 1 over F is equal to 1 over U plus 1 over V. Linear F is 10, and this is concave mirror. F is real, so positive. The image, we are considering the image to be real, so V is positive. So the linear magnification, which is V over U, please. In most times, I see students writing when they get virtual image minus V and all that. Please, this symbol here is an indication that we are looking at the absolute value, number, not any sign to this, okay? So 4 is equal to V over U. Therefore, V is equal to 4 times U. So we have 1 over 10 is equal to 1 over U plus 1 over 4U. LCM 4U. 1, remainder 4. So 4 plus 1. So we have 1 over 10 is equal to 5 on 4U. Therefore, 4U is equal to 5 times 10, which is 50. I'm not rushing to multiply. 4 will go into this 5. 4 will go into 2 will go into 10, 5. 2 will go into this 2. So I have U giving us 25/2. And class, what is 25 divided by 2?
12.5.
This is 12.5 centimeter. Let's see if this value will give us a real image, which is magnified. So object distance is 12.5. F is equal to 10. What will be the value of R? What will be the value of R, class? If F is 10, what will be R?
20.
20 centimeter. So looking at the object distance, F value, and R, what do you think will be the position of the object? What will be the position of the object on the principal?
Behind the focal point.
Behind the focal point, or
between the focal point and the center of curvature.
Center of curvature.
Exactly. Okay. So the moment you get details, you must be smiling to the bank. Gideon, your hand is still up. It's a mistake, I know. Okay. So when you sketch something like that, you must be able to tell. So the mirror is here. If this is the focal point and this is C, then the object is between, can be any. Hey, please mute yourself. Okay. If you haven't muted, do that. Else you'll be saying a lot of things. So there's the object O. And if an object is located between C and F, what is the nature of image form? Okay. The image will be real, magnified, okay, inverted, and formed behind C. Now, let's consider when it is virtual, because we are considering both, because concave mirror forms a virtual image which is magnified and a real image which is magnified. So if the question is stated and it is not clear, then you must consider it when virtual and when real. So when image is virtual, we are still using RP. So under RP, since the image is virtual, then V would be equal to minus 4U. It's still a concave mirror. F, under this convention, F is positive, but the image is virtual, so V will be negative. So using 1 on F is equal to 1 on U plus 1 on V. We are 1 on 10 is equal to 1 on U minus 1 on 4U. This time LCM 4U. This will go into it 4 minus 1. We have 1 on 10 equal to 3 on 4U. 4U is equal to 3 by 10. When we divide through by 4, we still have U giving us 15 on 2. This is 2. This is 5. Okay. Class, what is 15 divided by 2?
7.5.
This is 7.5 centimeter. Now, let's compare. So U is equal to 7.5. F is equal to 10 centimeter and R is 20. Class, how do we describe the position of the object? Where is the object placed?
It's in front of the focal point.
Specifically,
The focal point and the pole.
exactly, between the focal point and the pole, because object distance is less than the focal point. And we know that that is the only situation where concave mirror forms a virtual image. So the image will be virtual and also magnified. So this is how I was expecting you to have thought through the question. If you solve it one-sided, you get one-sided mark, half. You wouldn't be awarded the full marks. Please, is that clear?
Yes, please.
Is there any question? So whenever questions are given, you must be very, read it carefully to understand what goes into it. Gideon, I saw your hand being raised.
It was a mistake.
Okay, it must continue to be a mistake. All right, now we started with refraction of light. Refraction of light last time. And so quickly, let's go through. Angie.
So please, I have a question.
Go ahead.
So please, you gave us some formulas the last time that we can use, and one of them was like U is equal to F into bracket 1 plus 1 over M. So can I just use that one instead of finding U is equal M is equal to U over V and then substituting?
You can find that. You can use that as well.
Okay.
Okay, so
Thank you.
all right. We define refraction in several forms. One, refraction is the bending of light from one medium into another medium due to difference in the optical densities of the two media. This is based on the concept that class, whenever light is traveling in a homogeneous medium, and a homogeneous medium is a medium whose density does not change, constant. So when you on a torchlight and the torchlight is moving through air, it will just go straight without bending or getting deviated. But the moment the same torchlight hits a transparent medium, then the path of the light will change. So refraction can be said to be the bending of light from one medium into another medium due to difference in the optical densities of the two media. So we are doing this using angle. Don't forget that change direction is angle. We can also define refraction using speed or velocity. So refraction is also the change in the speed of light as it moves from one medium to another medium of different optical densities. So this time around, we are also describing or explaining the concept of refraction using change in speed. 3, we can also define refraction using change in wavelength. So refraction is also the change in the wavelength of light as it moves from one medium into another of different optical densities. And lastly, we can also describe the concept of refraction using the the refractive index, okay, of light, but refractive index of the medium. All right. So change in speed, change in direction, change in wavelength of light as it moves from one medium of different refractive indices. Here, the refractive indices actually has to do with difference in densities. So let's just focus our lens on these three. And so last time we saw that whenever light moves from one medium so this is a normal. So let air to water or glass. Meaning this first medium here is air and this one is water. So whenever light travels from a less dense medium into a more dense medium, what happens to the path of light? Yes, class. When light travels from a less dense medium to a more dense medium, what happens?
Say it bends away from the normal.
From the normal.
It is moving from a less dense medium.
Normal.
Yes, this is more dense medium. The path of the light must bend towards the normal. So the refracted ray bends towards the normal. So this is the incident ray. Incident ray. This is the refracted ray. This is the angle of incidence I. This is the angle of refraction R. Okay. Now, I is greater than R. So when we have this situation, the angle of incidence will be greater than the angle of refraction. Then velocity of light in air, V in air, would also be greater than the velocity of light in the water. So generally, whenever light moves from a less dense medium into a more dense medium, the speed of light in the less dense medium, okay, the speed of light in a more less dense medium is greater than the speed of light in a more dense medium. Or here we can also say that, or speed of light in water will be less than the speed of light in air. Just imagine yourself running from air even into a pool of water, or yes, where there's water and trying to run in it. You realize that the moment you get into the water medium, your speed would reduce. Okay, when you get into the water medium, your speed will easily be reduced. So speed of light in the water will be less than the speed of light in the air. Then the wavelength. Now, speed V is directly proportional to wavelength. Let's write this in words. Speed or velocity of light is directly proportional to wavelength of light in the medium. What it means is that if speed is greater here, wavelength would also be greater in the less dense medium. If speed is less in the more dense medium, wavelength would also be less in the more dense medium. In fact, whenever two quantities are said to be directly proportional, what it means is that an increase in one quantity also results in an increase in another. Okay, so if speed is increasing in another medium, wavelength would also increase. And if speed is decreasing, wavelength would also decrease. So lambda in air will be greater than lambda in water, or lambda in water will be less than lambda in air. Please, are we okay?
Yes, sir.
Recording in progress.
I'm coming in. Last time, I told you that frequency of light does not change from one medium into another. Please take note of that. Frequency, speed changes, wavelength changes, but frequency of light does not change from one medium into another. Does not change one medium into another medium. So, as physics people, we have this equation which connects speed of a wavelength, and frequency. You see, V is directly proportional to lambda, and V is equal to a constant of proportionality times lambda. This K is the frequency. So for every wave, its frequency is a constant. Please, Eunice, mute yourself. Eunice, I'm getting a very bad feedback here. Let me rather mute or good. Now, when the wave, Eunice, when the light is moving from a more dense medium to a less dense medium, which is air. What happens?
The light bends away from the normal.
Yes. So this time around, the light bends away from the normal. So this is I, and this is R, angle of refraction. So here, I is less than R, and V in water will be less than V in air, or the other way around. And the wavelength of light in water will be less than the wavelength of light in air. All right. Then we discuss the laws of refraction. We discuss the laws of refraction. Unit is giving me very tough feedback here. Eunice, can you hear us? No, she's not even close to the gadget. Please mute yourself for me. Okay, okay. Okay, so we discussed the laws of refraction. And the first law, Graham, quick. So the first law of refraction says that the incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. But class, do not forget that whenever light incident on a transparent medium, reflection also occurs, but the reflected ray is weaker. So we have a very weak reflected ray, but the refracted ray will be stronger. So this is the reflected ray, but very weak in terms of intensity. Then this is the refracted ray, but it will be stronger in terms of its intensity. Still, laws of reflection is obeyed. Angle of incidence is equal to angle of reflection. Then the second law of refraction is what we term as Snell's law. Okay, so the second law of refraction is the Snell's law. What does the law say? What does Snell's law say? Snell's law. Yes, Alikem.
Mistake.
Okay. Snell's law states that for any pair of media, the ratio of the sign of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant for any pair of media. The ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Mathematically, we say that sine I over sine R is equal to a constant. Okay, it's equal to a constant on condition that the refractive indices of the two media are different. So provided the material's optical density are different. Provided the optical densities of the materials or of the two media are not the same. Gideon.
So does it mean in the first formula you just give us, the V equals a constant times lambda? So that's how we are going to find our constant.
No, it is an equation we often use for the speed of light or wave frequency and the wavelength. I just wrote this to let you know that here F, since V is directly proportional to lambda, and when we introduce an equal to sign, we have K lambda, where K is the frequency. Frequency is just a constant. Are you okay? So that is why the frequency of light does not change from one medium into another medium, but its speed or velocity and the wavelength changes. Please, are we okay?
So please can you explain it again? Why it does not change for when it's transition to another medium?
Frequency of light is a property of the source of light, not of the medium. It's a property or a function of the source of light, not of the medium. So the medium does not have any effect on the frequency of light. Okay. But the speed of light is a property of the medium within which the light is passing. When the medium is less dense, meaning there are fewer particles of the medium within a given volume or area, the speed will be more. When the medium is more dense, meaning there are more particles within a given volume or area, the speed of light will reduce. So is its wavelength too. Angie.
But sir, the speed of the light can also be a constant in some cases. that in this one it is the frequency that is considered as a constant. I
No,
just wanted to be sure.
you see, it is similar to we as people. Whenever you are running in air, you don't feel any opposition. But attempt running in water, you cannot. This is because water is denser than air. So the density of the particle or of the medium will reduce your speed. And that is what happens to light traveling in a medium as well. Are you okay? But the frequency of the light will never change no matter the densities of the medium. And are you okay?
I was rather asking like, but the speed of light is always constant. It's like it's a universal constant. So I was asking, and that one also.
No. A speed of light in air or vacuum, which is a constant. Not speed of light in air or vacuum. Even in air, they are not the same, but the difference is not much. So we take the speed of light in air and in vacuum as almost the same. 3 times 10 exponent 8 meter per second. So here we are referring to speed of light in air or vacuum, not in all materials. Are you okay?
Okay, sir. Yes, please.
Eltonam, Jude, and Co. Hayfron, are you there?
Yes, sir.
So this constant.
Yes, sir.
This constant is what we refer to as a refractive index of the denser material, or let me qualify it, the absolute refractive index of the denser medium. Absolute refractive index is actually represented by the symbol, okay, mu or nu. So this N-like symbol or U, usually as students, we simply, because we want to always be free from this torture of the symbol design, we simply write N. N is equal to sine I over sine R, where N is the absolute refractive index. We can also use mu, which is sine I over sine R. So the choice is yours in using the symbol. Now the other thing we must understand is that what do we mean by the refractive or absolute refractive index of a material? Class, absolute refractive index of a material is the real or the actual refractive index. So absolute refractive index is also known as the real or actual refractive index of a material or of a medium. Now, the refractive index of water, mu of glass, is around 1.5. And the refractive index of water is 1.33. and the refractive index of air or in vacuum is equal to 1.00. What does it mean? So if the refractive index of a material is this, then it simply means that glass. So if the refractive index of glass is said to be 1.5, what does it mean? It simply means that glass can bend light 1.5 times as air. Glass can bend light 1.5 times as can be done by air. So we are always comparing. Okay. Glass can bend light 1.5 times as can be done by air, or glass can bend light 150% times as can be done by air. That is basically what it means. So if a material is denser, it also means its refractive index must also be greater. Look at air. 1. Water is liquid. Air refractive index greater than that of air. And then glass is solid. Air refractive index is greater than all of them. Okay, so refractive index actually goes with density. If the material is denser, its refractive index must also be greater. Gideon.
So when the refractive index of glass is 1.5, so when it's bending a light, does it bend the light towards the normal or away from the normal?
So it depends on where the light is coming from. We just saw that if the light is from less dense medium into the more dense medium, then it will bend it towards the normal. Okay, and if the light is from more dense medium glass into a less dense medium water, water or air, then it must bend away from the normal. So it depends on where the light is coming from. Class, are we okay?
Yes, sir.
Okay. Do we have any further question? A minute.
No.
You will not give me a minute. I'm coming. Now, class, let's also understand what we mean by absolute refractive index. Absolute refractive index. Of a material. And that is what we are representing by the symbol N or mu. So if you see N or mu, class, we are referring to the absolute refractive index or real or actual refractive index of a material. Okay, the actual. When we talk about absolute refractive index, class, it is the refractive index of a material when light is traveling from air into any denser material. So for absolute refractive index, it is absolute, or it is a must that the part of the light must come from air into another dense material. So the absolute refractive index of a material is the refractive index is the actual or real refractive index when light travels from air into any dense medium. Okay, so for absolute refractive index, light must actually travel from air into any other dense material. So for instance, if this is air and this is water, when light travels from air and then comes into the water medium, then we are actually referring to the absolute refractive index of the dense medium, which is water. Giovanni.
Sir, please, can the refracted ray bend to the extent of going beyond the normal?
No. It must always be from the normal to the refracted ray. So here, in determining the refractive index of the dense medium, we have the refractive index as light moves from air into what? Water. So from air to water, then because the first medium is air, then we are talking about the absolute refractive index of this dense medium, water. And we can determine that by sin I, Snell's law, ratio of sin I over sin R. Another way of expressing absolute refractive index is using speed of light in the first medium and then the second medium. So absolute refractive index of this can also be speed of light in air divided by speed of light in the dense medium, in this case, water. Another way of expressing absolute refractive index is using wavelength of light in air divided by wavelength of light in the dense medium. in this case, water. So these are different ways of expressing absolute refractive index. Absolute refractive index can be expressed as this letter N or mu having indicated the first medium, which must be air, and the second medium, which in this case is water. Or we can simply represent absolute refractive index as the symbol N or mu.
Sir, please, the formula for finding the the refractive index. Can you say refractive index?
The absolute refractive index.
Yes, please. Can you say it's equal to real depth over apparent depth?
We'll come there.
If you are giving those in the question.
Yes, we will get there. So it can be N is equal to sine I over sine R, or N is equal to speed of light in air divided by speed of light in a medium. Please, speed of light in air is always represented by the letter small letter C. Then we can also express absolute refractive index as wavelength of light in air over wavelength of light in a medium. We'll come when we get to refraction, and we'll talk about this. Okay, so these are different ways of expressing absolute refractive index. Now, the absolute refractive index of any material is greater than 1. The absolute refractive index of any material or medium is greater than 1. Why is it greater than 1? This is because, you see, whether we are looking at change in direction, sine I over sine R, you realize that for absolute refractive index, here the numerator, the angle of incidence is greater than the angle of refraction. And if you have a fraction whose numerator is greater than the denominator, then the overall results will certainly be greater than 1. Because if they are equal, it will be equal to 1. But the moment the numerator is greater than the denominator, it will be greater than 1. Then, if you use speed of light, you also realize that light has a greater speed in air than in any other medium because of the difference in density. So here too, the numerator is greater than the denominator, and so the results will be greater than 1. And the same thing applies to using wavelength. So absolute refractive index of any medium is greater than 1 because it is a ratio. The numerator is always greater than the denominator. So look at, hey, please, who is drawing on my board? Joshua.
Sir, please, I wanted to ask a question.
Do so.
Okay. Sir, it's about the absolute and refractive index of medium. Sir, so you said N is equal to sine I over sine R.
Yes.
Sir, so you said the numerator will always be greater than the numerator.
Yes, for absolute refractive index.
Okay.
So the angle
Yes.
of incidence is greater than the angle of refraction.
Okay, sir.
Are you
Sir,
okay?
so that
So we also have a question. So we also have a
sir,
question.
Let him finish.
I'm,
Joshua, finish.
sir, so that means it applies to the speed of light in air and speed of light in water,
Yes.
and the wave of light in air and wavelength of light in water.
Wavelength goes with speed. So if speed is greater in air than in water, then certainly wavelength would also be greater in air than in water.
Okay, sir.
All right. Joshua.
Sir.
Hey, what's the name? Gideon.
Sir Gideon. Sir, please, my question was, sir, please, so does it mean the C over V, the C there means the sign I, and the V also means the sign R?
No, we are expressing absolute refractive index in terms of various parameters. I earlier told you that refraction can be defined in terms of change in direction. Direction is angle. Refraction can also be defined in terms of change in speed. Refraction can also be defined in terms of change in wavelength. And so we can determine absolute refractive index, which is the measure of the extent of bending, also in terms of direction, in terms of speed, and in terms of wavelength. That is why I've given you all these three formula for absolute refractive index. Are you okay?
So please, can you define the C and the V?
Where C is
what do you see there?
Where C is the speed of light in air or vacuum, and V is the speed of light in any other medium. So C is for speed of light in air or vacuum, and the V is the speed of light in any other medium aside air or vacuum. So please, yes, it's a very good point he raised. Define the letters. In physics,
Okay, sir, please, thank you.
Define the letters. Where C is the speed of light in air or vacuum, which is a constant, 3.0 times 10 to the power positive 8. And V is the speed of light in any other medium aside this one, air and vacuum.
Okay, sir, thank you.
You're welcome. All right. Is there any other question? So look at the absolute refractive index of glass. This is 1.5. 1.50. Absolute refractive index of water, 1.33. They are all greater than 1. Okay. Let's discuss other refractive indices. And here we'll look at reversed refractive index. Reversed refractive index. Now note that light obeys the principle of reversibility. Or light obeys the reversibility rule, that if you choose I angle of incidence, it will give you R angle of refraction. when you change the direction and then you give it R angle of incidence, it must give you I angle of refraction as well. So let me quickly draw a diagram. And then reverse the path of light. So this is the normal. Now we are incidenting. This time we are reversing the path. Earlier it was from air to water. This time we want to move the path of the light from water to air. So our angle of incidence in the denser medium is R. When the light emerges out of the denser medium and comes into air, how will it bend? Will it bend away from the normal or towards the normal?
Away.
Away from the normal.
Away
Okay.
from normal.
Okay, so it must bend. Why will it bend away from the normal?
So please, because
It travels from water to a less dense medium.
Exactly. So our angle of incidence is giving us I angle of refraction. Okay. And class here, I'm using I and R here. Ideally, angle of incidence must be I. Angle of refraction must be R. But I'm using the principle of reversibility that if an angle of incidence I is giving me an angle of refraction R, then when I reverse the path of the light and give it R angle of incidence, it must also give me I angle of refraction because of the reversibility rule. Let's use numerical values to explain this. Assuming I incident an angle of 30 degrees to give me an angle of refraction of 19 degrees. When the path of the light is from air to water, when I reverse the path, okay, from water back to air, then 19-degree angle of incidence in the water must give me 30-degree angle of refraction. So that is why I'm using R for incidence and I for refraction. Please, are we okay? Class, are we okay?
Yes, sir.
Yes, sir.
Angie,
So please, must the more dense medium be at the bottom?
we
Like anytime
are reversing. We pick from air to water. And when we are reversing the path, it's from water to air. So from less dense medium to a more dense medium, when we are reversing, we are picking it from more dense medium to a less dense medium. Are you okay? Angie, are you okay?
Yes, please.
All right. Now, we want to find the refractive index. Now, note that the moment you reverse the path, and it is now traveling from a more dense medium to a less dense medium, it is no more absolute refractive index. It is no more absolute refractive index. because for absolute refractive index, the light must actually move from air to any dense medium. But the moment you reverse the path of the light, we term this as the reversed refractive index. So still, the symbol for refractive index, absolute refractive index, N, but the path is from water to air. If it is absolute refractive index, it is a must that the light must come from air to water. But the moment you reverse it, it becomes reverse refractive index, which is now sine R. We are applying Snell's law over sine I. For absolute refractive index, this would have been sine I over sine R. Class, are we okay here? Are we clear here?
Yes, sir.
Can I move to the next page?
Yes, sir.
No,
Hello,
please.
hello, Frank.
Sir, please, can you explain the reverse?
Mate Frank. So I'll look at it again. Are we done writing? So I move to the next page.
Yes, please.
So
No, please.
hey, you should have hurry up. Ohima, are you here?
Sir, please, I have a question.
Ask.
Sir, please, if refractive index is R over sine I, sir, please, what is the relative refractive index?
Oh, we will come there. You said I'm building it up gradually. Okay. I've talked about absolute.
Sir, so please, they are not the same thing.
No, they are not the same. We are building it up gradually.
Okay, thank you.
So we've talked about absolute refractive index.
Okay, please.
We've also just talked about reverse refractive index. We'll talk about relative refractive index. So let me explain the reverse refractive index once more. So we have there's a boundary or the interface between the two media. There's a normal. So if this is air and this is glass, so when light is propagated from air into a dense medium, any dense medium, we know that the light will bend towards the normal. This is I, this is R. If we want to measure how much bending has actually occurred, then we take the refractive index as light travels from air into glass. The fact that the first medium is air gives us what we call the absolute refractive index of the dense medium, which is glass. And we can determine that by writing the first medium and then the second medium, or simply the symbol N or mu. N can be determined using the ratio, Snell's law, ratio of the sine of the angle of incidence to the sine of the angle of refraction. We can also determine this using speed of light in the first medium, ratio of the speed of light in the first medium to the speed of light in the second medium. We can also find the same thing by lambda in wavelength of light in air divided by wavelength of light in the second medium, which is glass. This is absolute refractive index. Absolute refractive index. So for absolute refractive index, it's a must that the light must come from air into any other dense medium. Now, what happens when I reverse the path of light? So the same thing, I'm going to reverse the path. Before, the light was traveling from up, down. This time it's going to be down, up. And that is what I mean by reversing the path of light. So this is glass. And this air. Now, from the principle of reversibility, if I angle of incidence is giving us R angle of refraction, when I change the path, then R angle of incidence must actually give me I angle of refraction as well. So and this time, this is, oh, my diagram must be a bit accurate. So it must bend away from the normal. So look at how I'm reversing the path of the light. So our numerical value of angle of incidence must give me I numerical value of angle of refraction. If we, okay, so in terms of values, assuming I is 30 degrees, R will be around 19 by experience. So if I incident an angle of 19, it must give me 30. Okay. Now I want to take the refractive index. And this one, because the path is reversed, we call this as the reversed refractive index, as light travels from glass to air. And this is also equal to sine R over sine I. In terms of speed of light, we can also pick this to be V over C. C is reversed, where V is the speed of light in glass, C is the speed of light in air. We can also express this same thing as lambda in glass, the medium is glass, divided by lambda in air. This is reversed. This is reversed refractive index. Please, Ezagoma.
A.
Okay. This is reverse. Now, reverse refractive index is, on the other hand, always less than 1. This is always less than 1. And absolute refractive index is always greater than 1. This is because of the change. All right. I hope you're okay. So if it is from air to water, the absolute refractive index will be air to water, and its reverse refractive index will be water to air. Now, note that the product of the absolute refractive index of a material and the reverse refractive index is always equal to 1. The absolute refractive index of glass, A to glass, times the reverse refractive index, okay, from glass to air, is equal to, this is sine I over sine R, times the reverse refractive index of glass, on the other hand, is sine R over sine I. They will cancel and the results will be equal to 1. If you want to use speed of light, then the absolute refractive index of glass, air to glass, times the its reverse refractive index is equal to, this is C over V. When you reverse, the reverse is equal to V over C. They'll also cancel out and the result is 1. So take note that for any two media, the product of the absolute refractive index and its reversed refractive index is equal to 1. So the product of the absolute refractive index and its reversed refractive index is equal to 1. So generally, we say that the refractive index, as light moves from 1 to 2, times the refractive index as light moves from 2 to 1 is equal to 1. So 1 is the first medium, 2 is the second medium. When you reverse the path, 2 to 1, and you multiply this refractive indices, the product is always equal to 1. Please, is that clear?
Yes, sir.
All right. Now, let's look at relative refractive index. The word relative means a state, talks about a state of comparison. Yeah, we are comparing. Relative refractive. Ella.
Please, could you go back to the previous slides? Please, I want to capture.
Okay. Is this the previous or previous?
Thank you, sir. Thank you, sir.
Okay. So relative. Let's assume that I have two different media. This time, two different dense media, okay, such as water and glass. And I'm told that the absolute refractive index of water is mu. Let me use what you've also been using. Yeah, please give me a minute, I'll be with you.
Oh, I see.
Oh, that review thing.
We are told that the actual refractive index of glass is mu W. Please note that you can decide to use either N or this U-like symbol. The choice is yours. This is the actual refractive index of glass is mu G, meaning these are the absolute refractive index. This is the normal. So the path of light is from water to glass. Will it bend away or towards the normal? How will it bend?
Towards the normal.
Towards the normal.
So yeah, because glass is denser than water. So this is I, this is R. Now, one of the rules we have under refraction of light is this. If you have any two composite media for any two composite media, the word composite here means joined. So we are joining water and glass. How we join it is our own cup of tea. But we are joining water and glass. So for any two composite media, when you take the refractive index, the absolute refractive index of the first medium, mu of the first medium, which is water, and multiply that by the sign of angle of incidence in that medium, it must be equal to the product of the refractive index of the second one, mu of G, and the sign of the angle of refraction in that second medium. Every angle of incidence would give a certain angle of refraction. So for any two composite media, the product of the refractive index of the first medium and the sign of the angle of incidence must be equal to the product of the refractive index of the second one and the sign of the angle of refraction in the second one. Okay, technically what it means is that if you multiply the refractive index, absolute refractive index of the first one, and the sign of the angle of incidence, this must be equal to a constant value. A constant, it can be any number. Let's assume that this constant value is 1.2. When you multiply the refractive index of the second one and the sign of the angle of refraction produced, it must be equal to the same value, the same constant value, 1.2. So if they are giving you the same result, then you can say that this is equal to this one. That is why we are equating them here. Please, are we okay? Class, are you okay?
Yes.
Oh,
Yes, please.
Yes,
all
sir.
right. Now I want you to help me out here. From this equation, this marked equation, I want you to make sine I over sine R the subject. Help me make sine I over sine R the subject.
So please, you get mu G over mu W.
Okay, more views. So just do write that in your notebook, and then either you also share with me or you just follow that with us. We'll be doing it eventually. So okay, so from this equation, I'm making sine I over sine R the subject. So mu W times sine I is equal to mu G times sine R. So to do this, I must first divide through by sine R, and also divide through by mu W at both sides. So this and this will cancel. So I have sine I over sine R equal to mu G over mu W. Now, look at what we have here at the left-hand side. What is sine I over sine R? Evelyn, help me. Evelyn, Eltonam, what is sine I over sine R? What concept are we applying here? sine I over sine R. What is this? Evelyn, are you there? Okay, Hebron. Nana Hebron.
Say please, Snell's law.
Snell's law. We are applying Snell's law here. Okay. We are applying Snell's law here. So this can be also expressed as the refractive index as light moves from the first medium, which is water, to the second medium, which is glass. The left-hand side, which is sine I over sine R, can also be expressed as this. The refractive index as light moves from water to glass is equal to the ratio of the refractive index of glass, okay, to the refractive index of water. Giovanni.
Sir, please, when we did the refractive index using air and water, we saw that uh, the wavelength of air was the numerator and the wavelength of the water was the denominator. But here, when it came to the relative refractive index, the refractive rays were the glasses, and the in the incident ray is where the water is, but the wavelength of water is the denominator, and the wavelength of glass is the numerator.
Please, this is not wavelength. Oh. This is absolute refractive index. I earlier told you that absolute refractive index can be this sign or this sign. I am much used to this one. That is why, but this is the same as mu G over mu water. The wavelength symbol is like this. Giovanni, are you okay?
Yes, sir.
So get the difference for me. Okay, so this is what we call as the relative refractive index of glass with respect to water. So N mu G is the relative refractive index of glass with respect to water. Where the with respect to parts implies the first medium where the light is coming from. Okay, so with respect to water means that the light is coming from water to glass. So the relative refractive index of glass with respect to water is equal to the absolute ratio of the absolute refractive index of glass to the absolute refractive index of water. So you see, I earlier gave you the refractive indices of glass and water respectively. So if I'm looking for the relative refractive index of glass with respect to water, it will simply be absolute refractive index of glass is 1.5 and absolute refractive index of water is 1.33. So when I divide, whatever I'll have is the relative refractive index of glass with respect to water. So whoever asks the question about relative index, relative refractive index, with relative refractive index, we are basically comparing the absolute refractive indices of any two dense medium or media. We are comparing the absolute or the refractive indices of any two media. Okay, so for two media, different media 1 to 2, we can say that the relative refractive index is the absolute refractive index of the second medium N2 divided by the absolute refractive index of the first one. Look at what we have here. Water to glass. It is absolute refractive index of glass divided by absolute refractive index of water. So this second medium divided by the absolute refractive index of the first medium. That is it. This is the concept of absolute refractive indexes. Please, are we okay? Frank, are you okay? Frank is not being frank with me.
Please, the 1.50 and the 1.33, are they constants?
They are constants. I'll give you the absolute refractive indices of some substances, okay? They are constant. All right. Class, is there any other question?
No, sir.
Okay, so if there is no question, class, you spare me the remaining 5 minutes. Truth be told, I'm very, very tired. So this is where I draw the curtains on today's meeting. Thanks for your time, your contributions, and everything. We'll continue this wonderful session or class next week. Omega next week. Until then, in fact, take care of yourselves and bye-bye. Please subscribe to the channel. I need your subscription. I know you've been doing that, some of you, but if you haven't done it, please, I need you to do that for me, okay? And share for me as well. It will do me a lot of good. In fact, good night to all of you.
Bye-bye.
Bye-bye.
Bye. Good night.
All right, okay. Tasha, leave my board alone. You are writing on my board.
No, bye-bye.
All right.